So what happens if we have more objects to choose from than what we're choosing? And so what we're going to say is we're going to look at the number of permutations taken so many at a time. So we're going to go back to something that we did in our counting principles. And we're going to choose the digits, 4 digits, in a combination. And so we could choose from 0 to 9, so there were 10 altogether. And we said, hey, if there were no restrictions, it would be 10 times 10 times 10 times 10, because our fundamental counting principle, and we'd have 10 to the 4th possibilities, or 10,000. All right. All right, because I could have 0, 0, 0, 0, all the way up to 9, 9, 9, 9, and so it's one more than 9, 9, 9, 9. But it matched our fundamental counting principle. And then we added this restriction. What happens if we can't repeat a digit? And so on the first one, we have 10 options. I'm just going to bring this straight down. Actually, let me move some space here. I'll go on orange. And so on the first one, I have 10 options, but I've gotten rid of one number. Whatever it is, I've gotten rid of one. On my second one, I now have 9. And then on my third one, I have 8. And then on my fourth one, I have 7. And we said, 10 times 9 times 8 times 7. Run over to my calculator. Here I run. 10 times 8. Let's see here. 10. Oops, turn it on. 10 times 9 times 8 times 7. And I've got 50, 40. So 50, 40, 5,040 different combinations I can get. It's a little more restrictive, right? So if I can't repeat a digit, I have this thing. Well, what we're saying is that I am selecting 4 digits from 10 where I have no digit repeating. And so what we're going to say is we're going to call this 10 permutations 4. And so we're going to say we have 10 things and we're going to permutate 4 objects across that. And this notation is usually NPR. And so in our case, N equals 10 and R equals 4. And the formula for it is going to be N factorial over N minus R, whatever that is, factorial. But let's not run and plug this into the calculator. Let's just look at what it does. So N factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Right, because we're using 10, so 10 there. And then in 10 minus 4 is 6, and so 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. And so what I've done is I've taken all the possible combinations of 10 digits, and I've divided it by all the possible combinations less 4. But look what happens. Those cancel, leaving me 10 times 9 times 8 times 7. And so what we can say is we can talk about making the choices, and what we can say the ways we can find. Let me get the wording in the book here. Right, we want the number of different permutations of n distinct objects taken r at a time, and so it's n distinct permutations of r events. Show you again how quickly things rise. And I do like this book example. I'm so going to stick with it. There are 33 cars in NASCAR. And generally, the technology of the car and the people driving them are quite similar. So the odds of people winning are fairly close. So how many combinations of first, second, and third will come up? And so this means, Bob, Tracy, and Jeff is distinctly different from Tracy, Jeff, and Bob, and so on. And so we want every possible combination of first, second, and third. So we're looking at NPR with n equals 33 and r equals 3. And so we get 33 factorial over 30 factorial, which is 33 times 32 times 31, right? Because the 30 is going to cancel everything else out. Or 32,736. So one race of 33 cars gives you 32,736 different possibilities. Well, so it doesn't take many things for our combinations, our permutations to rise quickly. Let's look, though, at letting technology do this one a little bit better for us, because our numbers get big quickly. So I had 33 cars, and so I'm going to go to math and probability, and look here, I have NPR. And so I wanted 33, and I was going to choose 3. And there's my 32,736. So even though we can do these calculations rather quickly, when the downstairs cancels out the upstairs, our technology has the way of doing this. And I really, really want to stress, because we're looking at probability spaces where our outcomes and our sample space are based on counting things, we're going to need to count distinct options that appear out of things. And so being able to count how many combinations we can see of something is variable. You bet on horses. Well, I don't bet, and you might not bet, but you can bet on horses in a trifecta where you determine who comes first, second, and third. If all the horses are relatively close to each other in probability, your odds are very, very extreme. In fact, I think 10 horses, picking a trifecta. So I think there's more than. See, I don't know how bad I am at horse racing. I don't know how many are in. I have 1 in 720 for the 3 horses that you pick, if they're all equally likely to win. And so our numbers rise quickly. Odds come up quickly, and the things we count and the probabilities we come up will rise their number of things quickly.